In the words of Grace Hopper, a famous computer scientist, the most damaging phrase in the English language is, "It's always been done that way." RISC is our way to show our commitment to challenge the status quo and push beyond the limits of convention. With these words, we will transition to our next speaker. I am pleased to introduce an esteemed member of our faculty, Professor Swaprava Nath. Professor Nath is an assistant professor at the Department of CSE here at IIT Bombay. His research lies at the intersection of economics and computation, with applications spanning social and industrial paradigms. His work has been published in top AI and multi-agent systems conferences. His accolades include Fulbright Nehru Postdoctoral Grant, TCS PhD Fellowship, and the Honorable Mention Award of Yahoo Key Scientific Challenges Program. So today he will be talking about multi-agent AI from a game theoretic viewpoint and show how robust AI systems can be built with such agent. So let's welcome Professor Swaprava Nath on the stage.
Thank you. Okay, so thanks for the great introduction and welcome you all. So this talk is going to be about artificial intelligence, which I think everybody is really very excited about. But with a small caveat that there is this multi-agent thing. And I'll give you examples and try to motivate why this multi-agent part is important. So I am Swaprava, I'm a faculty here. So the moment you think about artificial intelligence, what comes to your mind? Some random guesses? ChatGPT, great. Large language models, auto-correction when you type in, grammatical corrections, detection of faces and all those things. Now, if you have already known that area well, then you must have known that behind every artificial intelligence technique, there is an optimization problem that is running behind. So be it deep learning training, your deep learning is an optimization problem, and several other things which are all optimization problem. I will try to call that as a single agent problem. Why? Because you are given a bunch of data and you are trying to learn something from it. And in some sense, you are solving the optimal solution for yourself or maybe the person who is trying to learn. How is multi-agent systems different from them? So let me start with an example, and it's a very toy example. Don't take it too much to your heart, but this is how to introduce it. So imagine one kingdom. Here is the king and the queen, so the queendom. And both of them are modern kings and queens, so they have artificial intelligence at their hand, and they can design systems, so they can use AI for two different purposes: to develop better agricultural techniques, so maybe something to do, how to do a hybrid type of a crop or something else, or they can use AI for more not so nice things like warfare, developing guns or weaponry, aircrafts, so that you can actually attack the other nation and essentially try to capture that nation. Now, in this diagram, so you can see, and let's imagine, AI is definitely expensive and also time consuming. So you cannot really invest your resources and effort on both of them, both agriculture and war. So for simplicity, let us assume you can only spend on either agriculture completely or on warfare completely. No mixing is possible. Now the numbers, so I'll place some numbers in these boxes, and that is, you can imagine that how much amount of happiness, satisfaction, or let's say profit that they are going to get if these two individuals choose that pair of actions, right? So remember, there is a slight difference from the other type of AI problems that we discussed about. Here, the outcome depends on the pair of choices or the combination of the choices that all the players, so in this case 2 players, the pair of choices that they make, that gives out an outcome. So imagine if both of them had chosen agriculture or used AI for agriculture, both of them could have developed, they could have solved their food security issues, and then they get some amount of happiness, which I'm just quantifying by this number 5. The actual units or the numbers are immaterial. All that matters is how they compare with the other numbers. Now, if both of them go for warfare, of course, you can imagine that they will engage in conflict. So I have deliberately chosen the numbers smaller because now there will be a lot of destruction and other things. So your happiness or your profit will not be as high as if both of them chosen agriculture. A vastly interesting thing happens, a very curious thing happens when one of them chooses agriculture, the other chooses war. So for instance, in this case, these are symmetric cases. Why these numbers? Because if, let's say, the king chooses agriculture and the queen chooses war, then the warfare, so because king has spent no energy or effort in warfare, they won't be able to defend their own country. So with warfare, the queendom will actually rule over and essentially take care of all the agricultural produce that they have made. In addition, they will have additional land and maybe prisoners, etc. Okay, so they will have more happiness. So of course, on top of 5 that they have produced, they will also have something more. And the kingdom loses everything. They have lost their own maybe life and some land and all agricultural produce, everything. And the symmetric opposite thing happens here. Now, imagine you are the queen, and which of this agriculture or war choices would you have made? Just give a second, give a minute of thought, and think about what should have happened, you should have done if you are in the position of the queen. Assuming that you have no communication with the other country, and even if you communicate, then also there is a chance that the other country will not actually listen to you, or certain contracts will not be feasible to satisfy here. So what should you have done? How many are in favor of agriculture? Okay. Okay, so feel very highly optimistic person. Okay, so how many are in favor of war? Very good. Okay, so I don't need to take this lecture. Okay, so the reason here is the following. So yeah, so this is the problem, and the decisions have to be simultaneous because this is happening for a long period of time, right? So investing in agriculture or warfare takes a little bit of time, and you cannot suddenly switch between one from the other. So if you have already invested, you have to stay with that, let's say, for a year or so, right? So imagine the situation of the king, the queen. If the king chooses agriculture, what are the options that the queen has? So between agriculture and warfare, you can see. So okay, so I did not explain what these numbers mean. So this tuple, you can see that each of these numbers, the first number corresponds to the happiness of the queen. The second one is the happiness of the king, right? So everywhere that's the meaning of the number. So if you look at the happiness, so the first entry in that tuple is the happiness of the queen. So therefore, if you look at the situation where the king has chosen agriculture, the optimistic people who are sitting there, so if they're choosing agriculture, the queen should actually choose war because that's giving him more happiness, more utility. And here we are assuming, yeah.
Is this table known by both?
Yes, the table is known. This is publicly known. The numbers are publicly known.
What the other side is doing?
Doing is not known. They are trying to take this decision simultaneously. Yeah, so here we are assuming that everybody is self-interested. They only care about their kingdom or queendom, does not care anything about the other one. So that brings us to the warfare. Now, if you do the same thing, you apply the same logic on warfare, it's better to defend your country rather than getting ruled over by somebody else, right? So again, war turns out to be the outcome. So those majority of you who are actually warmongers, they were actually right. And like it or not, that's the prediction that we can give. In a situation where people are completely competitive amongst each other, the war, war, so we call this the strategy or the action war as a dominant strategy. The reason for saying that is that no matter whatever the other person is doing, it's still better to pick that strategy over the other one.
What is the cost function with the sum total of the happiness of both kingdoms?
The equilibrium would have changed. Equilibrium would have changed, certainly. Yeah, so these numbers I have chosen carefully. If the numbers were different, then yes, you can see that the equilibrium, the conclusion that I am making would have been different. But yeah, so here I am just trying to motivate one special situation where what is collectively optimistic is not the equilibrium outcome. And that is, okay, so we call this war, war, this strategy profile of war, war as the dominant strategy equilibrium. The first time that we are using this word equilibrium, and this is where the multi-agent part comes in. In multi-agent systems, we do not really talk about optimal solutions because there is no optimal solution here. If you say that agriculture, agriculture is an optimal solution, yes, they are collectively optimal, but they are not an equilibrium. So equilibrium is this war, war, and therefore in a multi-agent scenario, we will shift our notion from being that of an optimal solution to an equilibrium solution. So that's the first diversion that happens here. And one can see that the collectively best outcome is actually the optimistic solution, both being agriculture. And that essentially changes when you look at the self-interested agents. Now, so taking an inverse view of this, that how we actually design systems, if we want this agriculture, agriculture to be an outcome, or the equilibrium outcome, that is exactly what we are heading towards. Okay, so let me give you few more examples essentially to actually motivate this whole question. Okay, so adding resources blindly does not improve the society. How? So this example fits very well with the IIT Bombay campus. So let's say A is the location where all the hostel blocks are, and D is the location of all the lecture halls. And each morning, the students need to reach to their destination, their lecture halls for their lectures. And there are two possible paths, one via B, one via C. And these paths have certain things. Okay, so let's say for simplicity, I assume 100 students. Each of them have a vehicle, a bicycle, and they can bicycle through this path in two different ways. And there are characteristics, special characteristics of each of these roads. So this path, this road A to C and B to D are wide highways, maybe the larger ones where it does not really matter how many bicycles are moving there. It always takes 600 seconds just to go from A to C. Similarly from B to D. A to B and C to D are congested lanes, and if the number of vehicles increase, then it actually increases your travel time. So one vehicle going there takes 5 seconds, two vehicles 10 seconds, and so on. Right? So N2 is the number of vehicles that is traveling on these roads. Now, let's ask this question. So if you are the vehicle, one of those students who are riding a bicycle, which path should you have taken? Given that there are other people, everybody is trying to minimize the time to reach to their destination. Flip a coin, okay, so the first individual, okay, just flip a coin and go one of them. Now, suppose the moment you have started taking your bicycle, you have seen that someone is taking this other path, let's say ABD path. What should you do to minimize? You take the other path, right? So you don't conflict. The third one, again flip a coin. Fourth one takes the path which the previous person did not take, right? So in some sense, you are splitting this thing, and you can see that why this is an equilibrium the way we have defined it before. So when we have this original circuit, original path, so you can imagine the 50 vehicles will go on each of these paths, right? So what will be the total time, the time taken by each of these vehicles? 600 plus 50 vehicles going here, 850, okay? So 850 seconds for each of these vehicles. Okay, so now the IITB administration has decided we will have a teletransporter device. So the moment you are in B, you are in C. Okay, so this is a one-way traffic. So suppose I have a kind of a shortcut route which takes negligible time corresponding to all these other times. Now, can you tell me the same answer? What would be your choices now? The first one will take which path? A to B and then C, D, right? So yeah, so that will take just 5 plus 5. The second one will also take the same path. Why? So the second one, if takes this ABCD path takes, so now there are two individuals, so 10 plus 10, which is much smaller than 600 plus anything, right? So this is a one-way path, you cannot go the other way. So is everyone convinced that the second person will also take the ABCD path? So N1 is a number of vehicles which are traveling in that path. So that's what we are trying to find out, right? So let's say I'm starting with the first vehicle who is taking that path, so then it's just 5 seconds at that point. The second one is thinking about, so at this point everybody is thinking about whether to take that path. Yeah, so N2 is the number of vehicles on this path, so what will happen? So, yeah, go ahead.
Does the person at A know how many vehicles are between CD while he's at A?
Not at this point, but given that you can, right, I mean, even if you do not know that, you can at least see the path between A to B, right? Still, you should be choosing AB, right? Because, okay, so imagine the situation where 99 people are going through this path AB and you know this. You have just seen all the 99 people have gone before you. Would you ever take AC? Because 99 times 5 will still be smaller than 600. So you will never take this AC path, no matter whatever happens after B, right? So is that example clear to everyone? So what will be the final equilibrium outcome in this case? Everybody will take this ABCD path. Now calculate the time for that. Now 1000. Okay. So actually it's a bad design, right? So adding resources blindly does not improve your society. So this is one example. When you have multiple self-interested individuals, all of which are trying to minimize their time to reach the destination, you should choose this design of this teletransporting device in some place where you actually help the people and not reduce their time of traveling. So B, D, and AC are not used at all. Those resources are not used. And these are not toy examples. There are real-world examples where people had to break down a newly built bridge just to take care of the congestion. Okay, so design is important. That's what I want to drive home. Now, the question is, how do we design a better society? And that is exactly the other part of this talk, which is to design. So far we have given predictive guarantees. Now we are going to give prescriptive guarantees. And here, for simplicity, I am assuming that there is a cake that we need to divide. And you can imagine that this type of, instead of a cake, you can think of resources, spectrum resources, or any kind of divisible resources. And you want to do a fair allocation or fair division of this. What is assumed for this resource is that they are heterogeneous, which means that the equal amount, so if I cut a piece here and cut the same sized piece somewhere else, because maybe this piece has some cherries on top of it or it has more chocolate and you like chocolate, that piece has a different value, different happiness for you than something which does not have them, right? So it may always happen, right? So you cut the same sized piece, but you like one piece over the other. So that is heterogeneity in the resource. It is perfectly divisible. You can cut it in whatever way you want. And the preferences are differing. That is, the same cut piece of chocolate, I might not like chocolate that much, and you may be a fan of chocolate. So that piece is highly valuable for you and very less valuable for me. Right? So this is a differing preferences across different individuals. Now for simplicity, what we typically do is imagine this, this cake as a real line interval to make things simple, line between 0 and 1. And your valuation is like a distribution over this 0 and 1, right? And different people may have different valuations. The the size of the piece that you get, you just integrate over your valuation of that piece, and that is your total value for that piece. And what is now, and we are also going to use the normalization, that the total value for the entire cake, if you get the entire cake, that is valued 1. That is the normalization. Now, we have not defined what is a fair division here. So one can say that a fair division is where you get your piece which is at least more than the average. So you are satisfied because at least you got an average share, more than the average share. There is another notion of fairness which is called the envy freeness. So imagine somebody envies. So suppose there are 2 kids and the mother tries to cut this cake on the birthday, and one person gets a piece and complains that the other kid got a larger piece, or I like his or her piece more than my own piece. Then there is a situation of envy, and I want to ensure that that never happens. That is, everybody is at least as much happy as he or she would have got the other piece, right? So the value for, so here a little bit of notation, the value that you get for your own allocation, that is AI, is at least as much as your own valuation for the other piece, some other J. And this, if you can ensure for every agent, then you can say that this is an envy-free allocation. So for the simple example of 1 cake and 2 kids, can you come up with, I'm sure that, how many of you have siblings? So you have encountered this problem at home at some point of your life. So how did you solve this, or how your mother or father solved this problem?
One person cuts, another person uses.
Exactly. So yeah, so I'm just going to call, so essentially the answer that was given is essentially a solution for the 2-agent problem. I call it a I cut, you choose algorithm. So the mother says that one of you cut this piece, the cake, and the other person gets to choose first. And why does this algorithm work? So let's see why this, so my first question, is this proportional? How many thinks no? Why?
Because they are both trying to optimize for themselves. The person will cut will try to do it such that no matter which one he gets, he'll be happier. But the person who choose will definitely try to go towards the envy-free direction, where he'll try to choose the one which he values more.
So the first individual who is cutting exactly in half according to his view, right?
Yeah.
So
That is proportional.
That is proportional for him. And the other person gets, if there is a larger piece, he gets at least half of that, half of the entire cake, right? So the argument that you gave is actually proportional, right? So this is the same argument for proportional. So yeah, so imagine the situation that so here you know that when you are cutting the cake, you are not going to pick the first piece. So if you cut it unequally, there is a chance that the larger piece will go to the other kid, right? So you will cut it exactly in half according to your view. So if you like the cherry, maybe you will also cut the cherry in half. So you are equally happy with any piece. So that satisfies this proportionality constraint for player 1, the first player. And the second player gets to choose. So if she feels that there is a larger piece, then according to her view, she will pick that and she will be at least half happy, right? Okay, so is it envy-free? So use the same logic, you are cutting it exactly in half. So you are indifferent between these 2 pieces. No matter whether your sibling gets the other piece or you get this piece, doesn't matter. You are indifferent, you do not envy this part, any of these pieces. So player 1 is indifferent between these 2. The other player does not envy because he or she picks first, right? So the piece that she picks is at least as much as the other piece. That's why she has picked it, right? Okay, so this actually satisfies both these conditions, both this proportional fairness. So yeah, so this is an animation of showing how, so it might not be the physical half because these are valued half, right? So maybe this half, this part is half because you like chocolate and the whole chocolate portion is on this part. And something else which is not very valuable for you, okay? So it is proportional and it is also envy-free. I don't really have time to explain so this is for cases where actually you have a divisible resource, but you can actually extend these ideas for indivisible objects as well, and let me just skip that. That's where we are. So with these examples, I hope that I am able to communicate to you that a game, the way we define game in game theory, is an interaction between multiple agents, all of which are trying to maximize their own happiness. In this terminology, we'll be using the term utility. And the game theory part, that is the first part where we were trying to predict what will happen in that game, is predicting the outcome of the game. And therefore, it's a predictive approach. And in the later parts where we are trying to design, let's say, how to cut this cake in a fair way, that is falling under this paradigm of mechanism design, where we are trying to give a prescription, how you should design this algorithm such that certain good things happen, fairness happens, many other things happen. And the applications, so these are toy examples, but the applications are many. So in the mechanism design, you will see this Google, Facebook. The moment you search for something, you get certain types of ads. Maybe you have purchased a ticket for a destination. The very next time you see different ads on different pages is about the destination of booking hotels in your destination place. How did they know it? Because you have while booking, you have given your Google email address, and that email has come, so they are processing it and gathering the information that you have actually purchased a ticket, let's say to Goa, and they start showing you ads, hotels in Goa, tours and travels in Goa, and so on, right? So those online advertising, so what happens behind the hood is there are certain advertisers, the hotel owners or the travel owners. They pay Google the moment you click on one of those ads. And they want to show, they are essentially trying to buy your eyeballs. And that is exactly how this online advertising works. The other brilliant application is stable matching. So the matching of the students to universities, hospitals, to doctors. All these things are situations where every individual has some self-interest, right? So the hospital wants to get the best doctors, the university wants to get the best students, and the students also want to get into the best university. So you need to have some sort of a stability in the matching that you are doing. It should not happen that the university and the student would like to break away. So after this, the declaration of the results are made, the assignments are made, they will break away and go to a new assignment. That should not happen. That is the idea of stable matching. The idea of stable matching is also used in human organ exchanges, and this is a very exciting area. So kidney exchanges, so you know that kidney, a typical human being can survive with only one of the kidneys, and depending on various things like maybe you want to donate one kidney to one of your relatives who have lost both the kidneys, but you do not match medically. So there are lots of things, that blood group and tissue type and so on, that you do not match, but you are a willing donor. There might be somebody else who is also looking for a kidney, and their relative also does not match. So this donor and the patient pair, you can consider as one individual who are actually looking for a donor. So if you have a situation where your relative can actually donate to that patient, and that patient's donor is also medically able to donate you, then you are actually saved. Both these lives will be saved. And that is exactly what this kidney exchange algorithms do. Maybe you have a cycle where you can donate all these things, and then finally you have all this person's lives saved. So how do you do this? There is a huge amount of literature, and there are, in certain countries, there are algorithms run by the nation which actually runs this kidney exchanges or organ exchanges things. Federated learning, so this is a new paradigm. So in federated learning, so the Google keyboard that you use, you can see that the moment you start with your Google keyboard, it's actually not giving you suggestions or autocorrections that well, particularly if you're using some Indian languages. But over time, it is learning, getting smarter and smarter. right? So how does it do? Maybe there are different other users who are also using the same language, and in a certain way, they are collecting all this information, the learning at a central place, and that language model is then pushed into each of these devices, right? So this is the whole idea of federated learning. Now, the question is, again, why should people contribute? So maybe this is a very simple example, but think of a medical situation where everybody has some medical data and you want to learn the right model for disease prediction or disease recovery, but that might require a lot of data. So some hospitals which has a lot of medical data will only contribute to that federated learning process if they get some payoff out of it. And if you just use the federated learning as it is, there might be a possibility small hospitals which do not have sufficient data, they might just free ride on the data of the others. So this is also an exciting area of incentivizing federated learning that's happening for the past few years. Peer grading, let me talk about that offline if you are interested. Airline scheduling. So many examples where you can actually have this kind of a strategic behavior. At the same time, you have certain components of learning or artificial intelligence, but you also need to take care of this fact that people are self-interested, and all that you can get is an equilibrium outcome and not a optimal outcome. Yeah, go ahead. So game theory is about multiple players. So yeah, so we are trying to give an equilibrium.
It is only for 2 participants. That's why it is equipped.
Oh, no. So the examples that we have just given is only to illustrate, because I can only show 2 players here, otherwise it will get confusing. So yeah, so any number of players you can include. Any other questions? Okay, so yeah, I'll not get into any further details, just want to show that there are certain, so in our group, there are certain interesting areas of research in all of these areas, but in particular, these auctions, which we have recently worked with 2 of our students. So if you are a student who are interested, I urge you to take a look at our group's website, talk to some of the students. I can see Drashti there. Can you just, yeah, so you can feel free to talk to them during the, I'll definitely be around, but also talk to them. Vidit is also there. Can't see anybody else. Ram, no. Okay, so yeah, so please feel free, and also attend all the student poster sessions, student talks. So there will be much more interesting things, and I welcome you all to take a look at those group websites and talk to all of us. Thanks very much for your attention.
Thank you, Professor Swaprava, for such an insightful talk, very interesting examples. We would like to express our gratitude to Professor Swaprava with a token of appreciation. I'd like to request Professor Bhaskaran to do the honors. Thank you, sir.